Record before I try to make all this make sense for y'all. I know you've been struggling with it, but you really are now to the point where what I have to say will make sense. I hope. Okay. So somebody already asked a couple of things. Let's clean up as we go. So one was, were there any questions on how he got these? Right, this was his S1, this was his S2, this was S3, this was his S4. If he did his arithmetic right, then if I put 4 in here, I get 2 to the 4th, 16 minus 1 is 15, over 2 to the 3rd, which is 8. 3 times that, it agrees, right? S3, 3 times 8 minus 1 is 7. 2 to the 2 is 4, so that one agrees. Okay. So now the only dilemma was we didn't get the limit of that one. So let's look. 2 to the n minus 1 over 2 raised to the n minus 1. Well, if you remember with limits, and I know you do, then we can pull the constant out front. Limit of the constant times the function, same as the constant of the limit of the function. And now I'm going to do college algebra to this again. This is 2 to the n over 2 to the n minus 1 over 2 to the n minus 1. Now I'm going to do Talbert's rule, which is when you divide, you subtract. So it's 2 to the n minus n minus 1 minus 1 over 2 all raised to the n minus 1. Right? So same as just putting that back up in the numerator and switching the sign. So that's 3 times the limit as n goes to infinity. Well, n minus a negative 1 is just 2 minus 1 over 2 to the n minus 1. Well, this goes to infinity, so that part goes to 0. This goes to 2, so I've got 3 times 2, which is 6.
Part 3 is still not right.
For where? Here?
274, yeah.
You don't buy that.
Don't buy
It
it.
doesn't work for n of 1.
Well, we'll look at that one next. So, yeah, I mean, I have the advantage that I know that this guy converges and is not infinity, because I know the formula, which you're going to know here very shortly. But you're right; he's got trouble on his work there. That's okay. Okay, so questions on the first one. We know what the terms are. We know what the partial sums are. Why do I keep asking if the limit of the terms go to 0? So you're adding up a bunch of numbers, right? Sum of 3 over 2 to the n minus 1. From n equals 0 to infinity, right? There's another way to write this problem. Because that would be 3, no, n equals 1 to infinity, I guess. That would be 3, when I put 1 in, I get 2 to the 0, so 3 over 1, plus, put 2 in there, I get 3 over 2, plus put 3 in there, I get 3 over 4, plus 3 over 8, plus 3 over 16, plus dot, 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 right? Just a different way to write the same thing. What do you notice? What's common to every one of those terms?
That's 3.
The 3, right? So isn't this the same as this? Okay, so that teaches you one of the rules about series. If I wanted to write this as a series, what would the series be? Right. In other words, we could have just pulled this 3 out front, right? I wrote it all out. But when you have a constant times something in a series, you can pull that constant out. It's just factoring. It's just like factoring something out of a summation. Here's another trick that's worth knowing. What if I wanted, this is really what Corey was trying at. It's very common when students make mistakes that they're really, really, really close to a good idea. You usually make a mistake because you're trying something that's a good idea. I mean, think about Evel Knievel, right? Before your time. But he made a lot of mistakes, broke a lot of bones. It's because he's trying something worthwhile. I mean, jumping over the Grand Canyon. What could be smarter than that? Okay. If I wanted to start this at 0, what would go in here?
1 over 2.
1 over 2 to the n, right? If I started at 1, this is 1 over 2 to the 0. Well, if I start this one at 0, it's 1 over 2 to the 0. Right? Those are the same expression, aren't they? Okay, so you can manipulate these expressions. You can change where you start if you want to by changing this, which is what he was saying. He was saying, I'm just going to call this one a 0 equals 5, and a 1 equals 5/3, and a 2 equals 5/9, because then a sub n is just 5 over 3 to the n. And he liked that better. Right? That's basically what he was saying. I'm just going to resubscript them.
I know this might not be what it is. I know you started from 0, but it seems like it would be way easier to figure it out if you start from 1. I understand you can do it from either way, but it seems once you pull out the 0 first, then the pattern is easier to recognize.
Okay, so
Can we do that? Can we just pretend that we don't have a 0?
well, if we change where we start and we're looking at adding up all these numbers, right? You just want to ignore this one?
It'll make it way easier to figure out.
Well, if you ignore this one, since you're adding them all up, then and you can get the answer, you can just add 5 back at the end, right?
Exactly.
That's fine. In fact, that's one of the tricks we're absolutely going to be doing. When they don't start where you want them to start, and we've got a formula that says they have to start at 0, we'll just adjust. That is an important idea. Okay, let's look at what we got. Everybody agreed that he had this right once. I mean, I think he had a good solution to it, but it does have to match up with the terms we've got, or his answer's not going to work out. Okay, now, and the limit definitely still goes to 0. Now, but nobody agrees that he's got the summation right down here. So let's look at the summation completely separately over here. S1 is 5. S2 is 5 plus 5/3, right? S3 is 5 plus 5/3 plus 5/9. Well, kind of like what Nick's saying, why am I dealing with the 5 at all, right? It's in every single term and I can factor it out. It's not making this problem any easier. So, doing the same thing that Xavier did over here, that's 5 times 1. This is 5 times 1 plus 1/3. This is 5 times 1 plus 1/3 plus 1/9. The next one is going to be 5 times 1 plus 1/3 plus 1/9 plus 27, right? Right? That's what I'm trying to figure out. That's 5 times 1. This is 5 times 4/3, right? This is 5 times 13/9. This is 5 times 40/9. I really shouldn't. Let me not do it that way. Let me write it out. 3 plus 1 over 3. 9 plus 3 plus 1 over 9. 27 plus 9 plus 3 plus 1 over 27. Do you agree with what I've got? See where I got it? All I'm doing is common denominators, right? I need to change this to 27 over 27. This one becomes 9 over 27. This one becomes 3 over 27. This one stays 1 over 27, so that's what I have. Okay? Okay, so what this really boils up is 1 plus 3 squared plus 3 cubed is what I need, right? And 1 plus 3 plus 9, and 1 plus 3. What I really end up needing to solve this problem is the sum of the powers of the 3's.
You separate that out again. Take the 1 out of each one. Just leave the 1 out. Because it's a constant.
I mean, I have a 5 over 27 here. If I multiply that 5 through, I could drop that and then subtract 5 27ths. But if I want to ignore that 1, I can't completely ignore it, because if I pull it out of here, then I've thrown out 5 over 27, so I've got to add it back in. So I don't see an advantage of pulling it out. It's
No, not that one. I mean, the 27 over 27, pulling that out.
Oh,
There's a recurring 1 each one.
I see. Yeah, I see. There's a 1 in front of each one. Maybe, but if I can find a pattern for 1 plus 3 plus 9, the next one's going to be right. Well, then I throw out the 81. I still need to know what 1 plus 3 plus 9 plus 27 is. So they keep showing, they keep recurring. So let me. So I have had students find a pattern for this, because this is 5 times 1 over 1, and this is 5 times 4/3, and this is 5 times 13/9, and this is 5 times 27, 30, 40, 27ths, and this one's 5 times 190, 30 is 121. And believe it or not, every once in a while somebody finds a pattern for that through just brute force. But I'm going to show you a slick trick to find a pattern. What I need is a formula for 1 plus 3 squared plus 3 cubed plus 3 to the 4th, right? Equals something. Let's call it S. I mean, I really need it for up to n, so I can add up n of them. So let's Chris?
Would it, okay, I'm just like thinking what it may be. Would there be a factorial involved in the top?
Say again?
Like would the actual end of the factorial involved in the top? Like, so 5 times ace to the n, I guess, minus, or right side of my head, I kind of lost myself.
In factorial parentheses
Like, can
squared.
you do like
Yeah,
factorial to
in factorial parentheses squared.
Squared over n n squared.
Yeah, in parentheses.
That's what I was.
No, in
We know-
factorial parentheses.
I don't know the factorial.
Yeah, squared, yeah.
But it'd have to be to the power below the n.
And you just put n at the bottom, and the denominator is squared.
Well, now the bottom is 3, definitely 3 to the, 3 to the n minus 1, right? We know what the bottom is. Now, if I put, this is the first, second, third, fourth, fifth term, 5 factorial is 120, right?
Squared. Because see, like for the first one, it's just 1. For the second one, it's 4. I guess I'm kind of like confused because like as it goes up.
Yeah, but this definitely doesn't work, right?
No, it isn't.
3 factorial is 6, squared is 36, that's not even close.
Yeah, you're right. I'm sorry.
That's all right. It's worth a try. Okay, so if I multiply this whole expression by 3, what do I get? I get 3 plus 3 squared plus 3 cubed plus dot 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 plus 3 to the n plus 3 to the n plus 1. You believe that? I multiply this whole expression by 3, I get 3 squared, 3 cubed. This one, the one before that, right, would have been the n minus 1. So when I multiply 3 to the n minus 1 times 3, well, that's 3 to the n minus 1 plus 1, so that's 3 to the n. But then I get the last one times 3, gives me n plus 1 threes. Rip?
What I meant to say for the top, which I didn't specify, I didn't say right. If you put s of n minus 1